This conference will now be recorded.
Hello, everybody. Jordan Girth here from the National Weather Service Office of Observations. Thank you so much for joining us for the Satellite Book Club Seminar Series. This is session number 152. I hope your summer's going well. Today's presentation is titled, Why on Earth Are We Interested in Ocean Color from GEO? We're glad to have our presenter, Ryan Vandermeulen, with the National Marine Fisheries Service, Satellite Coordinator and User Scientist for NOAA's Geostationary Extended Observations, or GeoXO. The discussion today will be facilitated by Chris White, the Applications Integration Meteorologist from the National Weather Service Forecast Office in Huntsville, Alabama. As you just heard, this session is being recorded. There will be an opportunity for Q&A after the presentation. Please enter your questions in the chat and we will field them in the order they are asked. If you have not signed in with your full name, please specify your name in the chat so we can follow up if necessary. Please remember to check your spam folders for any announcements from the Satellite Book Club, on the Satellite Book Club or from our Tower S team. We'd hate for you to miss anything. We're always looking for future presenters. Please contact our Tower S team, Kashad Bowman and Emily Maddox, if you would like to share your research or operational problem with our attendees. The training team can help create training materials that may be unavailable or point you to materials you may be unaware of. Brian Mata with the Office of the Chief Learning Officer can help with that. And I'd like to thank our Tower S team, particularly Kashad Bowman and Emily Maddox, the Office of the Chief Learning Officer, the GOZAR, JPSS programs, and last but not least, Chris White for all of their support of the Satellite Book Club. And we are on location today, as it turns out. We have Kashad and Emily down there in Huntsville, Alabama. So we're glad to bring the Satellite Book Club on the road. Without further ado, let me introduce Ryan Vandermeulen, who is, as I mentioned, is the NIMS Satellite Coordinator and User Scientist for NOAA's GeoXO mission. His previous role as a research scientist at NASA lent a broad perspective on ocean color remote sensing, from instrument specifications to algorithm development, radiative transfer modeling, and end-user applications. Since joining NOAA, Ryan has been interested in exploring useful ways of merging multiple satellite and in-situ data streams to better inform decision-making for NOAA Fisheries. Beyond his technical role, Ryan strives to promote and develop materials that ignite the interest of a public audience in the science of our natural world. Ryan, welcome to the Satellite Book Club today.
Thanks, Jordan. And thank you all for inviting me to present at this seminar series. As you mentioned, I'm one of the user scientists for GeoXO, specifically for the ocean color instrument, which is going to be the topic of today's discussion. So I'm going to jump right in. You may have heard about the inclusion of an ocean color instrument on our next generation of geostationary weather satellites. I just wanted to give you all some explanation as to why this instrument is taking up precious mass, which of course translates to dollars, right? And why this is taking this up on the GeoXO platform, what we're going to use it for, and I'm essentially hoping after today you will join me in the cult of ocean color enthusiasts here. Let's see. So just for context, since I'm not talking to a room full of oceanographers today, I want to make sure I give kind of a 30-second overview about what exactly I mean by ocean color. So here we're looking at a satellite's view of the ocean after I've removed this pesky atmosphere that to me serves no other purpose than to annoy us satellite oceanographers. I'm sorry, but this particular scene was captured off of the Mississippi River Delta, so it's really dynamic. We have lots of materials coming out of the river that we can see, floating in the water, mixing with swirls of algae further offshore, and then we get these really clean, sort of clear blue waters as we get away from land. So these 5 panels to the right represent the corresponding intensity of visible light, the colors of the rainbow being reflected back to the satellite. And you can see that the shape of this intensity or its spectrum changes across these water types, right? In green waters, the peak of intensity is over the green portion of the spectrum and so forth. So if we're looking at ocean water anywhere on Earth, we're looking at a complex mixture of optically distinct dissolved materials and microscopic particles, sometimes macroscopic things like sargassum. They're responsible for changing the spectral reflectance signature of the water. And not everything has a color associated with it, right? Things like salt, dissolved gases, or nutrients, they don't directly change the color of the water, but they do have a direct influence on the biogeochemistry of the water. And that's really what we're looking at here. We're seeing sediment here kind of aggregate, as it hits saltier waters. We're seeing, dissolved materials from river water moving offshore, and the nutrients that it brings with it are fueling the growth of these enormous algal blooms. So while they're, if you scoop up a little bit of ocean water, these will be microscopic and invisible to us, but these teeny tiny floating particles of life are absorbing various wavelengths of light for photosynthesis, which not only serves as the origin point for the oceanic food web, but it's also responsible for giving us nearly half of our atmospheric oxygen and keeping our Earth temperatures substantially cooler as they suck up carbon dioxide and sequester it deep in the ocean as they sink out. So in our field of optical oceanography, we spend a fair amount of time characterizing how particles absorb and scatter light, both in the lab and out at sea with natural samples. And the idea is, if we can establish a clear relationship between these different compounds of the ocean and how they collectively influence the color of the water through an inverse process, we can then use the color information from satellites to globally map all these various microscopic components of the ocean. Now, how well we can separate out this information from satellites is largely reliant on how close we can zoom in to see the materials, the range and specificity of the colors that we're detecting, as well as the sensitivity of the satellite instrument. It is really a miraculous feat of engineering that we're able to do this at all. The technological capabilities have really grown exponentially over the course of my lifetime alone. But of course, scientists are never satisfied. We always want more. Quantum physics be damned. We want it closer. We want it more often. We want it to be the best quality that the laws of the universe will allow. Hence, NOAA's next generation of geostationary weather satellites on GeoXO plans to have ocean color capabilities on board. Now, the ocean sensor is called OCX. The vendor for the build has not been selected yet, so these are kind of preliminary attributes on the screen here. But at the requirements level, we're going to be scanning the entirety of the U.S. exclusive economic zone at a refresh rate of at least 3 hours, at a spatial resolution of about 300 to 400 meters on the ground, and hyperspectral coverage from UV to the near infrared, and high signal to noise ratio. And because we care about such things, we'll have low polarization sensitivity as well. Now, the ocean is a dark target relative to land or clouds. It's only 3 to 8%, of the top of the atmosphere signal. So given that we're in a very photon limited system here, a geostationary orbit is really the only way we can optimize all of these dimensions, the temporal, spatial, spectral, and performance simultaneously, because we have the luxury to dwell and actually build our signal. So I know that was a really brief overview of the instrument, but with the time we have today, I just want to focus on providing a definitive answer to the question, why OCX? Why do we need this? How is it going to help NOAA? How is it going to improve our knowledge of the Earth system relative to what we already do from LEO? So the remainder of this talk is going to focus on some of the tangible benefits afforded by sustained geostationary observations of ocean color. Each application that I'm going to cover here is kind of designed to be a bit of an elevator pitch. So if you're looking for more information, take note and we can discuss it more after the talk. So one of the biggest innovations that this platform would provide is that we're going to have a much better chance of seeing through pervasive cloud cover. I can't express enough what a big deal this is for us. For passive remote sensing of the ocean, clouds are the bane of our existence. To the right, I picked a random example of a snapshot of ocean color derived from Himawari. It's a cloudy Earth out there, but if we composite all the scenes from a single day, we get a much more cohesive picture of the ocean. composite over 3 days, and we have an almost completely gap-filled product, right? Right now, over the course of 1 day, NOAA can currently image only like 1 out of 5 of our US Pacific coral reefs because of cloud cover. This goes without saying, but it's really challenging to leverage the assets of remote monitoring tools if you can't actually sense the areas of interest. There's a lot of reasons why we care about mitigating clouds, but here's just one specific example that pesters us here at Fisheries. We have a lot of marine species in the ocean that are highly migratory. Whales, turtles, sharks, they do not care for our defined boundaries. They will waltz right into the middle of a naval exercise without a care in the world. So, NOAA Fisheries has established prediction systems meant to protect whales and turtles, avoid bycatch, or even predict favorable fish habitats for target species. This really helps us provide guidance to commercial fisheries, because what we don't want is an entire fleet or fishery being shut down early because they hit too many whales. So the system operates best by ingesting ocean conditions in real time. They're built for that. The models are built for that. But currently, we're relying on weekly or sometimes monthly averages of ocean color, just because of these cloud cover issues. So, long story short, dynamic ocean management really requires dynamic ocean measurements to meet that challenge. I like to kind of say, just like tornado tracking, it's important for us to have the most accurate estimate of location and the concentration of hazards to protect fisheries, human and ecosystem health. We're going to take a major leap forward with GeoXO by combining these new capabilities. That is, in having a wider spectrum of light and zooming in at greater detail, and doing so with the diurnal cadence. So this is undoubtedly going to improve our ability to detect harmful algal blooms, which are toxic not only to fish, but often humans as well. If we can tell decision makers where they're headed in a timely fashion with a higher degree of confidence, we can save a lot of money and mitigate a web of public health and fisheries issues. The economic impact from harmful algae, costs somewhere over 100 billion per year. This is money spent on health impacts, money losses due to tourism, recreational fishing. Toledo, Ohio will tell you very expensive water treatment if the toxins get into your water supply, shoreside monitoring, and of course fisheries closures as well. But this is no small feat. These blooms are really patchy, as you can see from this image here. They move quickly, both on the surface and underwater. And while they often have a unique spectral signature, it's not always easy to disentangle that from the background pigments that are present in the water using just multispectral measurements. So really all these dimensions are kind of working together here to improve our forecasting ability. We're going to go back to applications, but just let's talk some science real quick. Because fast observations are not enabled by LEO satellites, GeoXO is going to enable us to kind of move beyond studying the end member effects of the process and into the study and observation of the processes themselves. Biology in particular is not only subject, to move around with the currents, but the biology itself is fundamentally changing throughout the day. The pigmentation of phytoplankton, their position in the water column, how much carbon they're producing, how efficient they are at doing so, their health status, the dominant species present, all of this is subject to change on the order of hours as they interact with the sun and their changing environment. So it's really important to get this right, because the entire marine ecosystem is wholly dependent on the activity of photosynthetic algae. And as I mentioned before, they produce half of the oxygen we breathe and really play a critical role in our climate regulation. Simply being able to quantify phytoplankton productivity by actually observing their growth, as opposed to the enormous error bars that come with modeling this from a single snapshot in time, it's really unquantifiable in its benefit. Even if we don't get a diurnal time series everywhere all the time because of cloud cover, these types of data sets that we will collect will really help inform and better parameterize the skill and accuracy of our space-based models, even for the benefit of polar orbiting missions. Another cool science application from analyzing consecutive imagery is having year-round capability of tracking particles. We could do this by following patterns of spatial variability, and color is really the best tool for tracking a water mass. Temperature can work sometimes, but come summertime, your gradients pretty much disappear completely. So you can actually do this for every pixel in an image as well, and create surface current vectors, as I did here with some GOSI imagery over Eastern China. So at 300-meter resolution, that we'll get from OCX, this allows us to study processes happening on much smaller scales. And oceanographers generally work at larger scales than someone like a fisherman would be interested in. The way oceanographers look at the ocean is not unlike the way meteorologists look at the weather, right? Both are concerned with really large scale dynamics of heat, and pressure, and density. These are driving winds and ocean currents. This here, though, this is not large scale circulation. These are sub-mesoscale features occurring on scales that are relevant to someone on a 100-kilometer day trip that a fisherman might go on, right? So GeoColor is really a whole new toolbox here by which we can directly observe how these processes are impacting biogeochemistry and assimilate these data into our forecasting systems, so we can resolve and predict smaller scale features. The 300-ish meter spatial resolution and the high revisit time provided by GeoXO will also enhance our coastal water quality monitoring, especially in areas where urbanization and high nutrient runoff really directly influence the frequency and extent of hypoxia or low oxygen waters and fish mortality events. So where fisheries is concerned, if we don't include these mortality events into our predictive models, we really decrease the overall accuracy of our stock assessment forecast. We could also watch, land-based pollution events as they're unfolding. This is really critical in areas with coral reefs, for instance, where pollution can have a high impact on their health and overall function. Aquaculture is another aspect of fisheries where water quality is key. Shellfish really don't like freshwater inundation from massive rainfall events, but perhaps more importantly, fish farmers can't sell their product when shellfish accumulate biotoxins from certain types of algae. So having this better time, space, and spectral characterization from Geo helps in two ways. One, the spectral signature that we will get is going to help us make better informed decisions to, mechanistically decide where a closure should occur, not just on a whim because there's an area of high biomass. And two, this helps us really optimize a determination for how long that closure should last, right? And both of these represent potential for significant cost savings and some mitigation issues. I keep touching on this phytoplankton diversity here, but just like flowers on land come in all sorts of different sizes and shapes, some with very specific ecological niches, the same is true of phytoplankton in the ocean. Based off of their ability to capture light in different ways, how efficiently they do so, they occupy different parts of the ocean and they play very different roles in the ecosystem. Now, since different phytoplankton have different ecological roles, we include multiple phytoplankton types in our coupled predictive models for species like sardine and anchovy. Right now, these phytoplankton types are predicted somewhat ambiguously as a function of the total biomass or chlorophyll in the water. What a world it would be if we can take direct observations of hyperspectral ocean color to better predict phytoplankton composition. What this does is it improves our ability to document the shift of species in the ocean and predict the resulting impact on the food web and fishery production. Some phytoplankton aren't necessarily harmful, but just big. Sometimes there's something so big, like Noctiluca scintillans here, highlighted in red, that the only thing that can really eat them are sea jellies. These guys are such aggressive growers that, like weeds, they outcompete pretty much everything else in the water, including the other phytoplankton. Now there's no food to sustain the smaller copepod population, right? No small zooplankton, no food for baby menhaden, and we have the potential for a major fishery crash. I know this kind of seems like a bit of an oversimplification, but it's really not. This entire scenario has been playing out with increased frequency in areas like the Arabian Sea, due to impacts associated with climate change, and this is having a devastating impact on the livelihoods of local communities. So if you follow fishing tournaments, you may know that the stakes for winning these things could be pretty high, on the order of like a few $1 million. Fishermen actually pay third-party services to use ocean color data to help with their fish forecasts, so they can target hot spots like convergence zones or frontal boundaries. Anyway, these companies, there's at least like 6 or 7 of them. They're pretty excited about the prospect of ocean geo, especially with the sun setting on the MODIS sensors that they're currently using. And again, I'll just briefly emphasize that with OCX, we're going to be monitoring ocean processes on a more accessible scale that fishermen actually care about. There's also a whole division of the Navy dedicated to ocean optics. We met with them a few weeks ago, and they're actually really ecstatic to hear about GeoXO capabilities. And a lot of what they use ocean color for is to determine basically how far light can travel underwater for various applications, from diver visibility to optical communications. They want to keep their divers safe, so they also don't want to send them into a low visibility situation or areas with toxic algae. So as we walked through each of their applications, and I'm writing these down, it became apparent that you really need a dynamic sensor that does everything, right? Better space, better time, better spectral. While many of their operations, of course, are overseas, they're still excited about using this for domestic training exercises and monitoring and for testing out improvements to their forecast systems. This is my last point here. I've talked about how we'll make use of the technological capabilities of the instrument, but one thing I haven't touched on, another attribute of the sensor, is that it represents a sustained, reliable source of data for our users. Some of these technological capabilities may be supplemented by one-off missions from other agencies like NASA's PACE or Glimmer missions, but there are no succession plans in place. GeoXO is here to stay until at least 2055. The thing is, when we come up and deliver these new capabilities to our stakeholders, it's not really worth their investment to develop novel products and applications if they can't rely on this data in the long term. What's more is we need this long-term consistency to help get an accurate assessment of ecosystem shifts under a changing climate. Anyway, the sustainability of this program is perhaps an underappreciated but an important asset to our users. So I'm just going to end it on this screen here. I won't read through all of these, just kind of a summation of some of the benefits of OCX, and I am happy to take any questions or have a conversation here. Thank you.
Okay. All right. Well, thank you very much, Ryan. That was a pretty fascinating presentation, especially for those of us, I think, in the operational meteorology community. Some of this information will be very new, very interesting, and hopefully there are some people joining in, especially marine or coastal offices that may also have some interest in this, but also thinking, at least on the meteorological side, Ocean Prediction Center. But it's good to hear from someone in one of our sister doing work like this. Really interesting, great science. One of our sister agencies under NOAA. So I do have to make a few announcements here, I think, before we kind of get started with a broader discussion and questions and that kind of thing. So just to encourage everyone to please stay on the discussion as long as you can. We know some of you may be dealing with weather about to, and you got a plan for all that, but try to stay on as long as you can. We'd appreciate that. And also, please specify your full names, if you would, in the chat when asking a question. And also, when completing a feedback survey, post it here in the chat room. And let's see, what else do I got to say? So at the conclusion of this, Emily, she's going to post in the chat room the link to the survey. By the way, I did want to mention that we do have Kashad and Emily from Tower S here, and we're actually here in a bigger setting at the NASA Sport Room right now. I do also want to mention that a week from today, next Thursday, July 27th at 12 Eastern Time, Ken Sparrow, the NOAA VLab director, will be discussing VLab in the cloud for those who are interested in that. And also, please contact the Tower S team, and that's Kashad Bowman, sitting here to my left, and Emily Maddox out of you to my farther left here, for questions about the SBC, the Satellite Book Club, or for configuration of satellite products as they may appear in your menu in any website of your office. So Ryan, first I did want to say, yeah, that was really interesting. A lot of this is new information for myself and probably for a number of our viewers. There's a few comments in here. I will just initially begin by mirroring something and also providing what someone named Matt Morris stated in here. And he said, this is fascinating. I had no idea the intricacies behind accurate ocean colors and ecosystems was. So great presentation.
Thank you.
Do have another question, by the way, so I'll go ahead with this first question here from Scott Lindstrom. Is everything you've said about the ocean color also applicable to freshwater lakes? So Scott is up in Madison, Wisconsin, associated with SIM. So put another way, how does salinity affect all the computations?
Thanks, Scott, for the question. Yes, indeed, and I'm sorry I didn't highlight the lakes a little more in here, but that's something we're really excited about because some of our with some of our polar orbiting missions, especially when you're off nadir, your pixel size might be up to 4 kilometers or so. It makes it a little difficult to resolve anything but sort of the largest lakes, Lake Erie, Great Lakes. With this sort of smaller footprint here, we are looking forward to looking at more of these freshwater lakes, especially some of them have calibration sites, validation sites in them. Lake Okeechobee is prone to a lot of green algae outbreaks, Lake Erie as well, and it's challenging. I noticed that you mentioned about the salinity affecting the computations. I don't think the salinity doesn't directly, but one of the challenges that we face with freshwater lakes is the correction for the atmospheric component there, kind of removing that atmosphere. And essentially what we do, it's a little more complicated than this, but we try to go into the near infrared and all the way in the shortwave infrared to look for wavelengths that are basically, we can assume are being completely absorbed by the water. This doesn't always hold up, especially if there's a large slick of green algae or sediment or something like that. You can actually get some reflectance in the near infrared. But the idea is if there's no water signal there, this is all atmospheric composition, right? So we use this to sort of model the atmosphere and remove that. A lot of those assumptions we make about atmospheric removal are based on maritime aerosols. When you're in a lake community and surrounded by land on all sides, you get a lot of sort of more complicated aerosols. And it's one aspect of looking forward to being able to resolve things like nitrous oxide from another sensor on GeoXO, the ACX might be helpful in this way to help us get a little better resolution of the lakes. A lot of times we just don't even apply the atmospheric correction. We just correct the geometry for Rayleigh scattering and use that as algorithm inputs into freshwater lakes. But that's a big part of our applications, and I appreciate you bringing that up.
Thanks a lot for that, Ryan. So I'll go on to the next question here, just going through the chat here for the moment. And this was from Bill Schoberg. Without MODIS, hopefully users will turn more to VIIRS. So I guess MODIS is going offline here before too long. So what OCX would be the role of LEO OC capabilities?
Yeah, I think there's a really important role for LEO to still play here because of the one limitation we have with GEO is that we're only looking at the disk of the Earth from its vantage point. So we're focused on the U.S. Yeah, if we planted, I don't know how many it would take, maybe 5 or 6, equally spaced around the globe. That would, and they were all sort of the same instrument and connected. It would be nice to get sort of good global coverage, although you'll miss the poles as well. With GEO, they don't tend to, they're not really able to see that far up. So you're kind of stuck with that vantage point right at the equator. With the LEO sensors, it's very complementary of giving us a sort of broader global, perspective here. And we're concerned about that for, sort of the larger scale questions concerning climate change. And these smaller scale observations, fit into that as well. That's part of the puzzle, to sort of understand how these smaller scale variabilities, how this fluxes of material coming, into these systems because of increased flooding, because of increased, algal blooms and things, that has an impact on sort of the longer term, climate systems. I really view these as synergistic in every regard.
Thank you. All right, we have another question here from Daniel Gillies, I believe. Hopefully I didn't mispronounce that. Anyway, so I assume to apply OCX hyperspectral data, we need to have a reference spectral signal to compare the measurements to. Does NOAA already have a catalog of ocean color spectral signatures that we can apply to OCX observations to, or is there a plan to create one? I guess that's the first question. I'll stop there.
Yeah, it's a good question. I was actually part of a project in my time at NASA of trying to build up some of these spectral libraries. It's challenging to, the applicability of these is, it could be a bit challenging. The measurements are not easy to do for a true reflectance signature for what the satellite is seeing. It's a fully water column integrated. You're seeing over sort of an optical depth, if you will, sort of an integrated signal of how deep the photons can reach and be backscattered back. So what we usually do is measure the inherent optical properties of the water, absorption, how they're absorbing spectrally, how they're backscattering spectrally. And we plug this into radiative transfer equations and try to model what the reflectance would be. That's kind of handy because you can make, a handful of measurements and sort of model what it might look like at different concentrations. And then you can up your non-algal components, which tend to be somewhat spectrally flat, so they don't have a lot of bumps and wiggles to them. It's really those for lack of a better word, those bumps and wiggles in the reflectance spectrum are corresponding to pigments, various, by and large, throughout the ocean, various pigment expressions. So we do know that certain species tend to share certain, groups of pigments. We have a very large and continuing library of pigments that have been collected for decades through HPLC, and we're also starting to get better imaging spectroscopy where you can actually flow through water and capture images of the individual phytoplankton cells. You can get an idea of what the community composition is. There's still work to be done here. NOAA is working on spectral signatures for green algae and some for the microcystis, these really harmful algae that pop up in freshwater lakes, and trying to measure that in various ways so we can get firm grasp on the signal and try to build new algorithms with that. But you can take these spectral signatures and they're not, it can be really tricky. And one of the keys, is that it takes oceanography to do this as well. There are combinations of phytoplankton you can mix together that might give you similar output, right? You have to have some context to this and know, sort of what species tend to show up in your particular estuary. That is if you're working on a kind of a small scale. On a bigger oceanic scale, we can do a pretty good job of separating out some of the, the bigger players into broad categories. But, it's not just a spectral signature alone. You have to potentially take into account, the time of year and your, temperature as well.
Okay, yeah, I was wondering about the ocean temperature too. Meteorologists are certainly more accustomed to looking at and used to looking at, sea surface temperatures and that kind of thing for our applications. And, we have data sets that we use for that. So, but it was also interesting to note in your presentation that you can more easily track ocean currents due to some of these spectral signatures you see than you would through sea surface temperatures. I mean, you can kind of see motions if you loop it over time, the SSTs, but yeah, it was interesting. I wouldn't doubt at all that you get a better sense of ocean currents from these interesting spectral signatures that you all are seeing. So.
Yeah, and that's using multispectral imagery from GeoXO. I think it's like 6 visible wavelengths there. So I think having a more distinct spectral signature will grant us the ability to kind of have more points to assess where the variability is going and have higher confidence that pixel did indeed move from this point to this, and it's not getting confused with another.
Okay. Also, this is part 2. This is another question from David here, let me go back to this. So, is calibration challenging when you have to account for both the properties of the atmosphere and the ocean?
Yeah, it stinks. The calibration happens in several stages. There's sort of an absolute calibration that ideally happens on board if there's like a solar diffuser on board, or we can look at like Fraunhofer lines or something like that to try to get make sure that the sensor try to sort of track the sensor drift. We also do lunar calibrations for that, but we also try to do sort of a vicarious calibration on the ground. Currently within the LEO paradigm, we're using a site in the blue waters off the coast of Hawaii. It's a site called the Marine Optical Buoy, or MOBI. So it's really fairly clean waters there. It's a really high-end instruments that NOAA invests in, and we compare those measurements over time, and that kind of builds in some of the error in our assumptions for atmospheric correction. And essentially what we come up with is a gain factor. That's the fancy way of saying fudge factor to try to correct for some of those lingering uncertainties that we have. Of course, that's for an oceanic site. There are ongoing discussions of what this is going to look like for GEO. There are going to be 2 ocean color sensors, one on where it goes west and the other where it goes east is currently. So we'll be able to see the entire EEZ. Goes west, we'll have no problem seeing MOBI, but goes east, it'll be out of the field of view there. So we could talk about potentially cross-calibrating and having one vicariously calibrated and sort of cross-calibrate in clear blue waters, or ideally put up another vicarious calibration site. But yeah, it is nasty business trying to calibrate these things, and if something goes wrong with the onboard calibrator, with Modus Terra, we ended up having to basically cross-calibrate that against other sensors. Yeah.
Okay. Well, speaking for operational meteorologists, we understand fudge factors. That's okay. So Bill Scherberg does have another question here. Would you envision a joint GEO-LEO ocean color product?
Absolutely, and I think with the launch of PACE coming in January of next year, it's our first global LEO hyperspectral ocean measurements, and we're going to be leveraging the algorithm development coming out of that, the applications, and being able to really see how hyperspectral data can be useful in practice on this really large scale, and being able to by the time GeoXO launches, ideally this is just going to be something we can do to help improve and be synergistic with these measurements, and then zoom in on a smaller scale and be able to see the movement of water masses. So add this extra dimension of information. I definitely see a lot of joint efforts both in the validation activities for these sensors and really just in general algorithm development. I'm hoping that some aspects, ideally, of what we learn from GEO can help us improve LEO products, and then being able to use that information and then tell us something about what's happening on the other side of the globe where GEO can't see.
Yeah, very good. We have another. I was going to keep on with the questions. We got several of them here in the chat. So if I'm pronouncing this correctly, Zhang Qian Wu. I hope I didn't butcher that too badly or mispronounce that. But so does OCX observe which saline part of the ocean lakes or everywhere it can see?
Yeah, it's going to be, now, again, because we're in sort of a photon limited system here, if we wanted to look at the whole disk like the GOES imagers currently are doing, we'd have to look at only a few wavelengths of light. So if we're going hyperspectral here, we kind of have to narrow down the area that we can look at in order to collect enough light signal to do this right. So right now it's going to be looking at basically the political boundaries of the EEZ. And at least a 3-hour cadence to that, the entire EEZ, maybe hopefully better as well, but at least 3 hours, and that includes some of our larger lakes as well. So there is some adaptability to this potentially. I mean, if we get an oil spill, there's no reason why we can't go off mission and have ConOps sort of try to do a little better job of maybe looking at the Gulf of Mexico a little more frequently, or looking at a harmful algal bloom. There's discussions and decisions that have to go into that, and ramifications for sort of ruining the continuity of everything else. But it should be fairly adaptable within the ConOps.
Okay. And could you clarify what is the EEZ?
Oh, the U.S. exclusive economic zone. Just sort of, I guess, the political water boundaries, if you will, of that belongs to the United States. That includes our island territories in the Pacific as well.
Okay. Thank you. So this comment, well, yeah, there's a question in here. So this is from Lee Byerly. So can you comment on how partner user engagement may improve with OCX? And he says, for instance, some HAB bulletins for the Pacific Northwest are bi-weekly, having more up-to-date information to drive faster updates, for example.
Yeah, thanks, Lee. I appreciate the question. Yeah, I mean, at this stage of user engagement, we're certainly interested in unearthing what all these various applications that maybe we haven't thought of even that might be that this data can be useful for, so that we can kind of hit the ground running. I mean, by the time in 2031, when the first GeoXO launches, ideally we want to have these connections with the user engagement community. There are efforts to put up a whole network of flow cytometry instruments that look at phytoplankton community composition all around the continental United States. Having close engagement with them, and potentially even if they're piping data fresh at relatively low latency, because our latency should be much better by 2031 as well, in the order of less than an hour, probably much less. So being able to pull data from real time and from GeoXO and being able to match it up with what you're seeing on the ground is really going to be important. And this algorithm development never ends. It's like I said, scientists always want bigger, better. If we figured out the whole phytoplankton community composition paradigm tomorrow, we would just move on to something else. But it's a big question as it is. So it's there's a lot of work to be done there. The more data, the better.
I'm sure you all are going to enjoy. You're kind of on the precipice of, I guess where we were sitting before GOES-R era here in our own community, and awaiting the much greater data volume and imagery volume that we got, 60 plus times what we had before that era. They could look at really more interesting sorts of satellite channel combinations and more rapid viewing and higher resolution. So anyway, I'm excited for your community about this. I see Jordan. I think he's about to kick us off here. Is that right, Jordan?
Never gonna.
Anyway, it's okay.
Never gonna kick anybody off. I think we got through all the questions though, right? We weren't gonna. I didn't want to just leave one there if there was.
There was V. Wegman there. Just says a bill to add blended geo LEO SST products are among the most popular, if not the most popular ocean products offered by Nestis. So.
All right. Well, thank you so much, Chris, and thank you so much, Ryan, for the presentation today. I really appreciate it. Seems like a lot of people are interested in what we can do from geostationary orbit with ocean color. And thanks to all of you for being with us. I hope you are able to join us next Thursday, July 27th. The Satellite Book Club continues with Ken Sparrow, the NOAA VLAB director, who is going to talk about VLAB in the cloud. So exciting Satellite Book Club presentations continue next week. And as always, if you have any questions about the configuration of satellite products, Gashad and Emily can help address those. Or if you're just interested in the Satellite Book Club, their email addresses are there on the screen. So we'll wrap it up for today. Once again, thanks everybody for attending. Thanks again, Ryan, for that great presentation. Thanks to everybody for the engagement. And thanks to Chris White for facilitating. Until then, take care.
Everybody, thank you.